So before the midsem, we had started discussing about distortion, right? Any questions on distortion?
Different from noise.
Is distortion different from noise or any comments? Anybody? So distortion is unwanted. That much we understand. Noise is also unwanted. Does that mean that both I can treat similarly, or there is a difference in?
Noise always considered AWG.
So noise is random, but distortion is not necessarily random, right? Distortion is dependent on the input swing, right? Distortion is dependent on the signal that you have applied. If the signal amplitude is higher, distortion is higher. If the signal amplitude is lower, distortion is lower. But Gaussian noise is independent of the signal that you apply. It's there, right? And the second thing is that distortion is predictable because you're applying a signal. So you should know what its repercussions are, right? If the signal amplitude is high, you will have more distortion. If low, so it means it's predictable. So, but noise is not predictable. So you have to deal with it statistically, right? So in many ways, distortions is easier to deal with because if you're a designer, you can explicitly know what the response of the output will be if the input is this. So even though this is not a part of the course, many other topologies use this feature to cancel distortion. Yes.
Regarding noise floor, how technique is to define the noise floor in any system? Then how we can.
Okay, is your question what is the definition of noise floor, or how do we measure noise floor? Okay. So there are multiple ways of measuring. One is, firstly, the definition of noise floor is slightly sketchy in the sense that you can define noise floor in multiple ways. I would say the most genuine definition of noise floor is find out the power spectral density of the noise when there is no input. Right? You just turn on the system, don't apply any input, output of the system goes to the spectrum analyzer, and you are seeing ideally you're supposed to see 0, minus infinite dB, but you are going to see something. So whatever is the power spectral density of whatever you are seeing is the noise floor. Right? But what happens is that if you actually go to the spectrum analyzer, and this is now I'm talking, if you have not done measurement, probably you will not understand this, but if you have done measurement, it will make sense. Spectrum analyzers typically have a setting called RBW, resolution bandwidth. So which essentially means that it does not always show you per hertz noise. It shows you to some extent amount of noise integrated over some bandwidth. So that is the RBW. So if you are integrating noise over some bandwidth, naturally you are going to see higher noise. Right? And for example, noise over 1 hertz bandwidth will be less than integrated noise over 10 hertz bandwidth. Because you're integrating over 10 hertz. In one case, you're integrating over with only 1 hertz. Right? So you have to be careful for the definition of noise floor. Noise floor won't make sense unless you also mention over what bandwidth, whether you're doing per hertz or per 10 megahertz. Right? Ideally, it should be per hertz, but you have to check the equipment, what it is doing before explicitly talking about noise floor. Okay, fine. So let's start from where we left off. So I remember the last time we met, I talked about distortion in a wideband system, and I said that after midsem we'll start to also give you a framework to find out distortion for a narrowband system, because in a wideband system, the distortion the one feature of distortion is that if you have an input, it is at a certain frequency, the distortion terms will appear at the harmonics of the input. Right? You remember that? Because ultimately Taylor series expansion is vi squared, vi cube, and so on. So if you have input to be sine omega t, vi square will lead to 2 omega t, vi cube will lead to omega t and 3 omega t, and so on, right? Yes.
That is also based on the assumption that a transfer function of a, let's say, amplifier is of the form a into v plus a into v square. It could also be a into v raised to 1 by 2.
Right.
To V raised to 1.5.
Right. So, I mean, okay, that's a very good question. So he's saying that what if the transfer function is, for example, like this, right? So if, I mean, instead of writing transfer function, I can simply write, let's say 1 plus alpha x, something like that, right? So let's say this is 1 plus alpha vi. So let's say v naught is equal to 1 plus alpha vi and some k here to make the dimension dimensionally consistent. So I can replace this one also as a Taylor series, right? Right. So any continuous time function which is differentiable can be expressed in the Taylor series format. So essentially, which means that I'll always have harmonics. So that is why when you push in a sinusoid through any distorted system, you only get multiples of the fundamental.
So is it like even if we have a term which is not raised to an integer, that power will get broken down into different.
Correct. Yes.
things.
Correct. One might say this is the way we have defined, right? If I choose, just because we have chosen a sinusoid, and the characteristics of a sinusoid is its frequency, and the frequency is related to a polynomial. I mean, when you pass it through a polynomial, you get harmonics. Hence, you get this, right? You choose something else, you are going to get something else, right? So it's the relationship between that. It's basically how a sinusoid interacts with the Taylor series. And because all continuous time functions which are continuously differentiable can be broken down in Taylor series, hence you get harmonics. Okay, fine. So, before going into the narrowband system, I would like to complete how to deal with distortion in general, right, in analog circuits for any system, right, and then we'll go to narrowband. So now, before going into dealing with distortion in any system, the question might arise is that what is so special about dealing with distortion? Because ultimately I can break every function into a bunch of polynomials and then decide and then put a sinusoid and I'm going to get the coefficients, right? So what is so special that we have to separately talk about a different system? So the reason we have to talk about a different system is this. So let's say I have an amplifier which is nonlinear, and I call this, let's say, some function f of v, where this is the v. Then it's not a problem. I can always say that this is, if the operating point is around 0, if I'm talking about incremental models, then the operating point I can assume to be around 0. Then this can be represented as f naught plus, if this is v in f naught f prime 0, then v in squared by 2, f doubled as 0, and so on, right? So this I can do for any function. But the reason we have to take one more step is because in almost all analog circuits, you do not deal with open loop systems all the time. So in almost all circuits, you are going to have some sort of feedback. So what happens if you have a feedback? For example, let's say you have a feedback network, which is of this form. Assume unilateral signal flow. If this is Vi, this is V out. And assume beta is perfectly linear. Generally, in the feedback path, we assume, we design the feedback path to be such that there is absolutely no anomaly, right? There is no imperfection in the feedback path because that is what we are sensing. In the sensing path, if there is an imperfection, then your action will also be imperfect, right? So you have to sense properly before you take an action. So your sensing path is generally designed to be very, very good. So we'll assume for the analysis purposes that beta is perfectly linear. So this becomes beta times V naught. So this becomes Vi minus beta times V naught. Now you see that we have a problem because in most feedback loops, the forward path, you need to have an amplifier right? I mean, I hope this part everybody knows from basic control systems, right? So the forward path gives you the amplification, the feedback path gives you the tracking. And if everything is linear, and if you assume this is A, then you get V naught over Vi to be equal to A by 1 plus A beta, right? So I am assuming everybody knows this, right? Without solving for it. So if you assume that A beta is tends to infinity, or A beta is much more than 1, then this almost goes to 1 by beta. And since beta is perfectly linear, your V naught over Vi is linear, right? So now we are, this makes the assumption that A beta is much, much higher. And also this makes the assumption that we are not considering any distortion anywhere else. Okay. So now what we want to do is to go one step inside and not neglect the distortion terms. And the distortion producing term here is only this block, right? So given that we know what is the distortion component of this nonlinear block, that is, assume the distortion, that block is an amplifier, which is this, which means I know F naught, F dash naught, and F double dash naught, and so on. What will be the relationship between V naught and Vi with distortion, taking distortion into account, right? So that is what we want to establish, correct? So you should now be able to appreciate the fact that this is not a very mathematically trivial thing to do. Why? So how would you go about, let me ask you, how would you go about figuring out what, I understand maybe the zeroth order approximation is V naught over Vi is 1 over beta, right? If I neglect all distortion terms and I assume A beta to be much greater than 1. But if I have to figure out what is the contribution, what is the V squared term that is going to come, what is the V cubed term that is going to come, how do you go about figuring it out? So what is the mathematical framework you are going to use to find out V naught over Vi, taking distortion into account? That's the question. Okay, so tell me the first step. Of course, we have to use Taylor series. That's the only instrument that we have. But so where do we start? Note that I want to find out, in this case, I am looking for G naught to be equal to some function of Vi, V naught equal to some function of Vi. Correct? I know the relationship between this point and this point, but I want the relationship between this point and this point. Okay. So all I can, in the absence of any information, I can at least know that V naught is a nonlinear function of Vi, and it will be some other nonlinear function and not F. Correct? So I can, let's say I call this G of Vi. So I have to find out G of Vi. Correct? So now, first I want us to appreciate the fact that is there a mathematical difficulty in this? If there is no mathematical difficulty, the part that I'm going to say doesn't have any sense. So if we appreciate the fact that there is a mathematical difficulty, then the next part can make sense.
Is F of V naught?
No, here I just assume that if it is perfectly linear, then gain is A. I mean, don't consider this as is, right? So this is just to lead up to whatever we were doing. By the way, since he has asked, let me ask you one thing. If the gain, so if let's say this is, I call this VE, this is F of VE, I can express this in a Taylor series format, and I call this, let's say, F0 plus F dash VE, sorry, VE. So from this expression, from the one that I have written just now, can you tell me what is A? Can I find out A from this expression? Right? So this is the A, right? So A is basically the first derivative of the of the block, right? So that is important to understand, right? So this is, if when I'm neglecting everything else, which means I'm this is the quiescent term, right? So in small signal, we normally, if I move my axis to get rid of the quiescent term, then F0 I can assume to be 0, right? And all the other terms are distortion terms. When we do small signal analysis, we essentially neglect all these terms, and we only retain this, and hence we can linearize and all those things we do, right? So right now we do not want to completely linearize. We also want to understand the effects of the other terms. Okay. So now this is where we are. How should we proceed?
Instead of VE, we'll substitute VI minus F.
Correct, right? So instead of VE, we are going to simply substitute VI minus beta V naught, right? So your V naught should be equal to F of Vi minus beta V naught. And therein lies the issue. This becomes a transcendental equation, right? So you cannot really solve it as is. So hence you need a framework to solve this kind of problems. If it is a completely open loop system, then it's not a problem because nothing is fed back. So this problem is coming because the input is setting iteratively, if you can think, the input flows, creates a distortion term at the output, and the part of the distortion term gets fed back to the input, which changes the input to F, this nonlinear block, to some extent. It updates the distortion term at the output, and this keeps on iterating till you reach a convergence, right? So which means that every time you, in a continuous time system, all of this happens simultaneously. There is no if-then statement in a continuous time system. But if you are doing numerically, if you are solving for this numerically, how will you go about doing it? You will assume that the input is probably around the operating point. That is your first step. And then maybe Newton-Raphson method or whatever method you have learned in your UG, you take that assume that's the output, take the feedback part of the output, then you update the input to the nonlinear block, then you update the output of the nonlinear block, and you keep iterating till you reach, then you see that the output is not significantly changing between steps of this iteration, and then you say a convergence has reached, and that is the final output, right? So you see that there is a mathematically intensive thing to do, right? If in a circuit design, when you are a circuit designer, you don't want to spend so much time every time to understand how the output will look like. If I have a negative feedback system, right? I should be able to just look at it and find out how should it behave. At least have an easy framework to figure it out. So given that mathematical framework exists, but it's numerical, our job is to figure out how can I simplify this entire analysis to get a intuitive feel of it. Okay. So for that, what we need to do is to first develop a mathematical framework. So by the way, there is an extremely rigorous way of proving what I'm going to prove now. I will not get into that because that probably is half the course. It's called Volterra series method. What I'll do, I'll take this example, show you what the framework will look like. And assuming that that framework holds everywhere, we are going to generalize it. Okay, so what I'm going to do might seem rigorous, but it is not. Okay. Is the motivation clear? Now can I proceed? Okay, fine. So if the motivation is clear, that's good. So before I proceed, some things that we should be aware of. So firstly, one thing we are already aware of because it came out, for if everything is linear, then I know that V naught over Vi. So for linear system will be is equal to A by 1 plus A beta, where in this case, A is F dash 0, 1 plus beta dash 0. Fine. Okay. So by the way, I'm assuming we are linearizing around an operating point, right? So I'll also, because I'm always taking F dash 0, otherwise it has to be F dash that quiescent point, right? So I'm assuming linearization around an operating point. Okay, so this is something we are going to use. Another thing that we are going to use is this. So let's say this is perfectly linear, right? I call this A. And let's say I inject something here. And let's say this is 0. Input is 0. Okay. I am injecting something here. Sorry. I'm injecting something here within the loop and taking the output from here. So let me call this V inject. So what will be V naught over V inject? So should be pretty simple to evaluate. So V naught is here. So this is beta times V naught. So this is minus beta times V naught. So this is minus A beta times V naught. So your V naught essentially becomes minus A beta times V naught plus V inject, which means V naught is V inject by 1 plus A beta. Correct? So I'll write it in the form of beta F dash 0. Okay. So this is another thing we are going to use. So basically the thing that we are going to use here is what happens if I have an injection at the output of the amplifier, and while the amplifier is a negative feedback loop, right? So keep track of this expression. Okay, so now let's proceed. So this is again V naught times beta. This is Vi minus beta V naught. So now we will assume that just like here we assumed that A beta is much greater than 1, we will here also assume that F naught, this is the A times beta is much greater than 1, right? So why are we assuming this? We are assuming this because so if this is much greater than 1, then at a very crude first level approximation, what can I comment about this voltage? Let me call this voltage VE. E stands for error. Right? So yeah, so if ideally this if the forward path gain is infinite, right, or the loop gain is infinite, your error voltage should go to 0, right? So it will never go to 0 because your F dash 0 is not infinite. But I can say that this will be much smaller than VI. That much I can say, right? So if you are designing the system for whatever it is supposed to do, then VE should be much lesser than VI, correct? So which means that I should be able to, other than the fact that I am dealing with twice only incremental models, I can simply say that then this F of VE can be expanded around F of 0, right? Because VE is much smaller than VI, right? Can be expanded around F of 0, since VE should be much smaller than VI. Okay, so that is another assumption. And since now, since we are only dealing with incremental, again, since we are dealing with incremental inputs, so we'll consider that F of 0 is 0, right? And we'll also further consider that G of 0 is 0. G of 0 is where, yeah, so the definition is V naught is G of Vi, right? So we'll consider G of 0 to be 0 and F of 0 to be 0. Helps mathematically get sort of term anyhow, but there has some physical significance also. Okay. So if that is it, then let's proceed. So firstly, I can say that this is also a nonlinear function. So I'll expand this as g of 0 plus vi 0 plus vi squared by 2. I'm limiting myself to the second order expansion. I mean, for obvious reasons, otherwise it gets out of hand. But hopefully this will be sufficient to tell us where we were ending up, right? So if since g of 0 is 0, I will say this is equal to vi 0. Right, so this is one equation. And now I can also say that V naught is equal to f of this guy, right? F of Vi minus beta V naught. F of, okay. And so this, I have already established that this is, I can evaluate this guy around f of 0. So which means that I can evaluate this as Vi minus beta V naught f prime of 0. Because f0 is 0, I'm neglecting that term. Plus Vi minus beta V naught whole squared by 2. Fine. Which means that I'll take the first order term on the other side. So this becomes V0 1 plus beta F1. Fine. So it's good to pause at this point and stare at this term. What is this term? Yeah, this is V out by V in under what condition? Under perfectly linear condition, right? So this is the output under linear condition, under perfectly linear condition. Fine. So at least we are in the right track. We have got the main term. But the other terms we have to figure out. Okay. Fine. So let's figure out the other terms. So what I'll do is now, just like we have to do it recursively, what I'm going to do is I'm going to replace this V naught term with the expansion of in terms of this, right? And then I'm going to equate powers, right? So the standard thing to do. So just if I just write this Vi minus beta V naught whole squared, so I can expand it separately. So this is Vi minus beta, and V naught is Vi g beta 0 plus Vi squared by 2. Correct? Fine. So I'll take out only the squared terms because I want to equate the Vi squared terms with V naught, right? So okay, let me write it out explicitly, then probably it will make sense. So what I'm planning to do is that I know that V naught is G prime 0 Vi. This I know. And I also know that this is equal to this. Correct? So what I'm planning to do is replace this V naught with this Taylor series expansion of this final term, because this final term is only of Vi. It does not have V naught. and then plug this term into that square term on top, and then equate Vi square. Right? That's all I'm going to do. Right? So if I do that, what do I get? So from here, I get this is equal to, I'm only interested in the square term. So I'm getting one Vi square term, or rather I'll just write it here. Vi 1 minus beta G prime 0 plus, or rather minus beta Vi squared by 2. Correct? And if I expand this, I'm going to get only one Vi squared term. All the other terms will be higher powers of Vi. Okay? So I'll only take that term. This is approximately equal to Vi squared 1 minus beta G prime 0 whole square plus higher order. Okay? Okay. So I'm going to use this. I'm going to use this directly. So what do I get then? So I know that V naught is, okay, maybe you can write, then I'll move. Fine. Should I move up a bit? Okay. So I now go back to this equation. So which is V naught is the first term, which is Pi F prime 0 plus this Vi minus beta Vi V naught squared by 2 times that. So Vi minus beta V naught squared is what? If I only take the squared term into account, is this. So that is Vi squared 1 minus beta 0 whole squared. I had divided by 2 and I had something, right? F double dash 0 by 1 plus beta F dash 0. Plus higher order terms. Okay. Okay, fine. So it looks like we are getting somewhere. So what is this? 1 minus beta G prime 0. So I know what is G prime 0. G prime 0 is F dash 0 by 1 plus F dash 0. So this is beta, right? So this is 1 plus 1 by 1 plus beta F dash 0. Correct? So now we are there almost. So I replace this term here. So I get V naught to be equal to the first order term plus Vi squared by 2, then this 1 by 1 plus beta F prime 0 whole squared times F dash 0 by 1 plus beta F dash. Right? So effectively, this is whole cubed. I'm not writing in the cubic form, I'm keeping it in this form, but hopefully this should make sense. Okay, fine. So now this at least gives us a framework where this is the first order term, perfectly linear term, and this is the second order term while taking distortion into account. And you are obviously going to get third order. Now you can see that the algebra will become quickly more complex because you have to take more terms in that expansion. So that's why I'm purposefully not going there. So, so the key thing there are a couple of things to note here. One is that if I only concentrate on the distortion term, it seems like, by the way, there is a technical term for this thing called beta F naught 0. Do you know what it is?
Loop gain.
Loop gain, correct? So this is the loop gain. So it seems like whatever was the distortion term for the F"0 is the distortion component of the amplifier or the forward path. Correct? So whatever was the distortion contribution of the amplifier, it is getting divided by the loop gain cube. Correct? So you are seeing that there is already negative feedback is helping in suppressing distortion of the amplifier. Correct? So that firstly, that itself is a very useful thing that comes out of this analysis, that you can have a terribly distorted amplifier in the forward path. Moment you put it in negative feedback, under the assumption that the loop gain, taking only linear terms into account, the linear loop gain, if I have to say, even though that term doesn't exist. So that loop gain, which you get from the linearized analysis, that helps in reducing the overall distortion terms, which are not linear, right? So what is the takeaway when you are designing a negative feedback loop? If you have a terribly distorted amplifier, try to at least increase the linear gain of that amplifier, right? If you increase the linear gain of the amplifier, moment you take it in negative feedback, it is going to take care of the distortion terms to some extent, right? It is going to suppress the effect of distortion. So that is one key takeaway. Now, even though this is not a class where we talk about designing negative feedback loops, but the part that I would like to focus now is this. How do I make sense of this from a circuit perspective, right? So this is all analysis. Every time you do the analysis, you are going to get the right answer. But from the circuit perspective, how does it make sense? So for that, let me again go back to the thing that I asked you to pay attention at the beginning. If I have an injection here, this is grounded. What is this? Assuming everything is linear, V injection by 1 plus beta F. Correct? Okay. So this seems like, now what I am planning to do is to model this, whatever we have gotten here, model this as something that is getting injected here, right? So the purpose of that is I would want to understand, I understand that this term is the desired term. Okay. So if I say that I do the linear analysis of this network, applying VI here and taking the output, I'm going to get this term. There is no problem. I am bothered about finding out this term, second term. So given that I know the first term and I know the loop gain, even I'm only interested in finding out the second term, how can I find out the second term? Okay. So for that, all I understand is, since this is coming, or since everything is coming in this format, where it looks like I have VI squared times. So let's say I say that this instead of V in J, I applied an input which is VI squared by 1 plus beta F net 0. Right? If I VI squared by 2, 1 plus beta F net 0, let's say I have applied there. So what am I going to get at the output? Assuming everything is linear now. Yeah. So I'm going to get this exact term, right? I'm going to get VI squared by 2, 1 plus beta F naught 0. Okay, I missed the F double dash also here. Times F double dash 0 by 1 plus beta. Fine. This is what I'm supposed to get. Correct? So I'll just club these two here. So this is the injection gets divided by the loop gain. Correct? Is this fine? Okay. Okay. Which essentially means that it looks like I should be able, if I now stare at this equation on the top and this block diagram in the bottom, it seems like I can divide this analysis into two formats. In one form, I do completely linear analysis, where I assume that there is no distortion. And I get the first term, the one in the green box. And in the second analysis, I assume that there is no input. Input is grounded, right? And I assume that your amplifier is still linear. That's why I have f-0 inside. But I then assume that I am injecting some output, injecting some distortion, some error term at the output. And if this error term is of this format, right, then I should be able to get the output which corresponds to the actual distortion output when everything is put together. Right? You can think of it like a superposition kind of thing. I'm doing two separate analyses, even though it's not superposition. Okay, I'm doing two separate analyses, one completely linear analysis to find out the loop gain, and another, I modified the circuit in such a way that the input doesn't exist, but the circuit is completely linear, but I'm injecting some current, injecting some distortion term at some strategic places in the loop. Make sense? Or doesn't make sense? Doesn't make sense?
Okay. How we are making that thing linear, supposing it is not linear now?
It is not linear. No, this is the analysis hack. We are not making the circuit linear per se. We are trying to develop a framework in which I can find out the non-linearity easily. Nothing changes in the circuit. This is just analysis hack to find out the distortion terms easily. So what is the step one? The step one is find out the first term, where I assumed everything is linear, because linear circuit analysis is easy. And step two, I would still like to do linear circuit analysis. So I do not want to put distortion in the loop. So I made the circuit linear, grounded the input, and I'm applying an error term somewhere in the loop. The reason I am wanting to split this is that this error term does not get affected by the loop action. So earlier, the amplifier is embedded in the loop. So any distortion term also comes back, feeds back, and makes a mathematical nuisance. Here, I took out the error term and injected it in such a way that the error term does not get updated every time you go around the loop. Right? So hence, the mathematical analysis becomes easy. Okay, so that's the only thing that we are doing here. So this is called finding out distortion term using perturbation method or injection method. We're injecting the error at the output of your distortion producing element. So I showed it with only one example, but in a generic thing, you can show this with, if you have like n number of distortion blocks available, you do the perfectly linear analysis for all the blocks, right? You are going to get the operating conditions, you are going to get the linear term. And then from there, you find out that you add these distortion terms at the outputs of each of these nonlinear blocks, and then do again a linear analysis. Then whatever you are going to get will be an approximation of whatever you are supposed to get if you do a full-blown analysis. So it's better we do an example, and that would make things clear, right? So let's see. So by the way, here I showed it just in a block diagrammatic format that injection can be either voltage or current depending upon what you are interested in, right? So let's do a current injection example, because in analog circuits you mostly use transconductors. So we'll use a non-linear transconductor. Okay. So let's say we have a transconductor here. This is our VI, so V0. Let's say this transconductor here has these characteristics. This is VE, this is GMVE plus G2VE squared. Right? So this is given to us. I can characterize this transconductor separately, open loop system. We can do it, right? So now the question is, what will be V0 over VI? I understand that V0 over VI will have distortion terms. I want to estimate that. Okay. So what is the step one? I do a perfectly linear analysis, right? Step one is okay, fine. So if I do a linear analysis, what do I see? If this is V naught, this is V naught over 2. So this current is GM times VI minus V naught over 2, right? So GM times VI minus V naught over 2 flows into 2R to create V naught. So I get GM to 2R, 2 GMR times VI is equal to V naught 1 plus GMR, which means V naught over VI is 2 GMR by fine. A sanity check. If GMR tends to infinity, that is a loop gain tends to infinity, then obviously this is a virtual short, right? If there is a virtual short, then this becomes VI. If this becomes VI, this current is VI by R, which means V naught becomes twice V naught, twice VI, right? So that checks out. Now the next thing will be to find out the distortion term, correct? So to do the distortion term, what's the algorithm then? Firstly, we'll ground the input, correct? So we'll not change the linearized, we are not going to change the linear amplifier model. We are going to ground the input. Amplifier is still linear, but we have to inject something, correct? We have to inject something. What are we going to inject? Now, this is a voltage controlled current source. Everything is current that is coming out from the block. So we are going to inject a nonlinear current. Okay. So current injection is simple. You just put a I injection. But what will be the value of this injection current? That is of importance. Correct? So how do I know what is the value of this injection current? So let's go back and find out. So value of this injection current seems to be what? I should be able to inject. So VI squared will come as is, correct? F dash prime I know because F dash prime corresponds to the G2. Basically G2 corresponds to that second term, right? And I know the loop gain, correct? So I can inject that appropriate current at the output, correct? So by the way, F dash prime is not G2 because second term is supposed to have a factor of 2, right? So G2 is basically F dash prime by 2. So what is it that I'm injecting then? I am injecting this I injection should be equal to F dash prime by 2 is G2, VI squared times G2 divided by 1 plus loop gain cube, right? Because this is square and this is 1. 1 plus loop gain cube. And what is loop gain? Where it will be square?
Injected now. Output was that.
Correct. You are right. Thank you. Inject will be squared. And what is the loop gain? This denominator is essentially 1 plus loop gain, right? And if you're unsure, you break the loop and find out what is the return voltage. So it's GMR, right? So basically 1 plus GMR whole squared. Okay. So I know what is the current injection. Then I know what will be the V naught, right? So I know, now since this is already applied in the way that it has supposed to be applied, so I can do it anyhow. So this is GM. So So this is V naught over 2. So the current will be taken out because the positive terminal is grounded. So this is Gm times V naught over 2. So effectively, the current that is going into the resistor ladder is I inject minus Gm times V naught over 2 times 2R is essentially V naught. So I inject times 2R is V naught 1 plus GMR. So by the way, here the V naught is a second order term, only the distortion term, because we are doing distortion term analysis. And if you're not sure, it's better to mark it up. It's probably better to mark up. The traditional way of marking it up is this. You write it like this, where the subscript within parentheses means that it's not a square, it corresponds to the second order term. Okay. So I inject times 2R by 1 plus GMR, which in this case becomes VI squared times 2RG2 by 1 plus GMR whole cube. Fine. Make sense? Yes.
Injection.
Hmm.
In our analysis, when we have derived the expression for the distortion also, we have considered the input to be voltage and output also is voltage.
Yes.
But here it is transconductor.
Yes.
Input is voltage and output is current.
Yes.
That expression can be written directly like as we have.
Yeah. I mean, okay, I agree what you are saying. So that, see, I have done here, all the analysis has been done assuming voltage, right? So that's what I said. I just took an example and I generalized it. But in principle, you can write it. But whatever you are saying is correct. If somebody shows me the voltage one and that then goes to the current one, I would also be suspicious, right? But this is only to show you that it works. We are now generalizing this, even though this is not the correct way to generalize. We are generalizing and say that this is a framework, and ultimately currents and voltages are dual of each other. You can do the same thing. But I mean, hopefully this, forget about the derivation, right? Hopefully the framework that we got, the outcome of that framework gives us a way of simplifying the design and the analysis part of the design, right? Do we agree with that or do not agree with that? Don't agree with that. Okay, so maybe, if you do a couple of problem statements, probably it will become more fluent. But the key thing so if you do not agree with that, then what I would encourage you to do is to find out this same solution using full-blown analysis, right? So assume that this is Gm times VE plus G2VE squared, correct? And don't do whatever things we did. Just do full-blown, right? You are going to see that you are going to get a lot of terms, and eventually you are going to get to the right answer. But the amount of algebra you have to do will be like more than a page long. And this is only considering, I have only considered second order distortion here. If I have third order distortion and higher order distortion, it will become even more complicated, right? Another addition to, basically again, one leap of faith is, even though I showed the same thing with the second order distortion, we can do this with the third order distortion also and fourth order distortion also. But then the problem becomes that, and for that, every time do I have to go back and find out what is these extra terms and then inject? Actually, no. So there is an easier way to go about doing it, and that is as follows. So what is the root cause of this distortion here? The root cause of the distortion is that I am having some input voltage, finite non-zero input voltage VE, and that is creating Gm times VE plus G2 times VE squared. Correct? So if I can estimate VE, then I'm done. Right? If I can estimate the first order VE, then I'm done. I don't have to do higher order VEs also. Why? That assumption is valid because I am saying that VE is already a scaled down version of VI. Negative feedback ensures that VE is much smaller than VI. So if I can find out what is the first order term of VE, then I do not even have to do all these things. Correct? So basically what I'm saying, instead of finding out the current that is getting injected at the output and do it every time, I would rather find once VE and then inject the corresponding currents that arise due to VE. Right? So basically then what I'm saying is that if we find VE1, 1 as in the first order term, then I can basically model this as this is GMVE, that's a perfectly linear, and I have another term which is G2VE squared. Correct? And if it had G3VE cube, then I can simply add another term which is G3VE cube. Correct? So even the simplified things to do with respect to whatever we did till now is to find out the first order VE using linear analysis. Okay. So if we do that, what we get in our analysis? So what will be VE? So V naught I know, right? Which is 2 GMR VI by 1 plus GMR. So this feedback VF is then GMR VI by 1 plus GMR. And what is VE? VI minus this VF, which is VI by 1 plus GMR. Right? So what is the outcome then? If I know VE, I do not have to do all the other things that I am doing. I'll just say this is grounded, this is grounded, this is grounded. This is again GM, and I'm going to inject a current which is equal to GM times VI squared by 1 plus GMR whole squared. Sorry, I think I made a mistake. Times G2, right? Sorry, this is equal to G2 times. G2, let me take a step at a time. So this should be G2 times VE squared. This is VE. This was supposed to be the VE that we got from here. So this VE I get from here and plug it in here. Correct? So, and this VE is essentially VI by 1 plus GMR. VE is this, then you do whole square and do the analysis. So this is useful because if I have the third order term also, if I have this third order term also, all I have to do is not redo the analysis. I'll put another current source here and say this is G3 times VE, VE1, VE whole cube. And you keep on adding. So this is called method of current injection or perturbation method. Literature, different types of nomenclatures are used, but this is what the crux of the matter is. Okay. So now do you think it is a simpler method? Right. So you do two-step analysis. In one step, you do normal small signal analysis. Find out the incremental input at the input of your distortion amplifier, right? Then redraw the circuit, assuming the effective input is 0, but the actual input is 0, but the output of the amplifier is being injected by the distortion term, and the distortion term you have got from the previous analysis, right? And then do the linear analysis again. So the whole purpose is that we do not want to leave our linear analysis models, right? So all circuit theory courses we will take that if things become complicated, we always come back to linear analysis somehow. Find out a way of coming back to linear analysis, because that is something we can easily figure out. We do not have to even write out the equations fully, right? If I know that something gets injected at the output, I simply know that the output will be whatever is injected divided by loop gain and some scaling factor, right? So this also gives you a framework to understand what is the way to reduce the distortion. Reduce V. As simple as that. As a designer, you have designed a negative feedback loop. You have certain distortion at the output of a negative feedback. You need to reduce distortion. What do you do? This framework is simply telling you that reduce V. How do you reduce V? Reduce the linear V. How do you reduce the linear V? Increase loop gain. Right? And increased loop gain we can work with. Linear loop gain I can increase. I mean, we have so many handles, right, when you do amplifier design. So you are isolating your design thinking, right? Do not want to deal with distortion term, linear term, and everything together. You are isolating the thinking and say that, okay, this is the framework. Once the framework is done, you can also estimate how much is your distortion term, right? Obviously, you are going to characterize your amplifier in the open loop sense in the first place, right? You are going to have an approximate idea of what G2 will be, G3 will be. If you have that idea, then you simply plug in those values. This is even simpler because if GMR is much greater than 1, you don't have to deal with 1 plus, right? It's become VI by GMR, right? So you know that, let's say your GMR is 100. I have to reduce the distortion by a factor of 2 more. I make it 200, right? Second order distortion. If I have to, for third order distortion, the impact will be even higher, right? Because it goes as cube, right? And so on. Okay. Any other questions? We have about 10 minutes. We don't want to start another new topic. Okay, so if there is no questions, maybe I'll talk about the thing that I started to talk about in the beginning. What about, so this is a framework, right? This framework can be used anywhere because we have not taken any assumption of bandwidth or anything. So whether it will be wideband system, narrowband system, doesn't matter. This framework can be used anywhere. But if I come back to the question that I had started off with, that how do you design, what is the framework of design of estimating distortion in a narrowband system, given that in a narrowband system, if you put in an input at certain frequency, the distortion term will be a harmonic, which will definitely be out of band, right? What I mean by that is that, let's say you are designing a band pass filter. You are designing a band pass filter, which has op amps and everything inside. And this is centered around, let's say, 1 gigahertz. Okay. And you apply an input omega naught or rather F naught at 1 gigahertz. The fundamental will obviously fall here. You do linear analysis, you get the fundamental. The second harmonic will be at 2 gigahertz, right? So 2 gigahertz is probably here. Your amplifier does not work at, your bandpass filter does not work at 2 gigahertz, which means it filters out everything, right? So you'll be happy that it's a very good amplifier. Very good bandpass filter, no distortion, because no harmonics I can see. Okay, but is that correct? That's definitely not correct, because I have if I make a bandpass filter using amplifiers, I am going to see a distortion, right? Just that the framework that I have used is not enabling me to evaluate the distortion. So if the framework is the problem, then you have to change the framework, right? You cannot really say the amplifier is fine. And the framework that is used is, instead of applying a single tone, you apply 2 tones. Why 2 tones? That is going to get evident now. So let's say I apply, let's say I have a distortion framework, which is vector 0 plus, let me just simply write it out. So let's say V naught is equal to Vi A times A naught times Vi plus A3 times Vi cube. I'm purposefully taking A3 because it is going to help me establish what I'm trying to establish. We'll come back to the A2 later on. So, and let's assume that Vi is two-tone at, let's say Vp sine omega naught t plus Vp sine omega 1t, right? Or omega 1 and omega 2, let's say. And omega 1, omega 2 are near omega naught, right? Both are in band to your band pass filter. So what am I going to get at the output? I'm going to get V naught to be equal to the first term, which will be linear. So I'm not writing the first term. So this is linear term plus I'm going to get distortion terms. And what will be the distortion term? It will Vp cube will be anyways be there. Then I'm going to have sine omega 1t plus sine omega 2t whole cube. And if I expand only this, I'm going to get sine cube omega 1 plus sine cube omega 2 plus 3 . Fine. So this term, if I only consider, let's say this term, this is, I'm going to break up into one term at omega 1, another term at, by the way, here I have A3, another term at 3 omega 1, right? 3 omega 1, I don't have to bother because it is out of band, correct? Omega 1 will fall on top of my fundamental, correct? But the fundamental, if assuming A3 Vp cube is much lesser than fundamental, because ultimately you are planning to design a linear network, then maybe I can neglect this, right? Maybe, not always, but maybe. But that is also not the important point. The important point is this. So what about I concentrate on this? How do I break this up? I'll get two terms again. What are those terms be? So omega, I have sine squared omega 2. So this I can break it up into a DC forget, and one is 2 omega 2. Correct? I have 2 omega 2 and omega 1. So omega 1 plus 2 omega 2 and omega 1 minus 2 omega 2. Or I can also write in this format. Omega 2 plus omega 1 and omega 2 minus omega 1. Or 2 omega 2 minus omega 1. And given that omega 1 and omega 2 are near about omega naught, right? So let me just write it this way. Let's say omega 1 is omega naught minus delta omega, and omega 2 is omega naught plus delta omega. So this clearly is way outside omega naught, right? So I can forget about this. This does not help. Or what is this? This is 2 omega naught plus delta omega minus omega naught minus delta omega. Correct? So what do I get? Omega naught plus
Delta omega.
no, I get 2 here plus there 3 delta omega. Correct? So this is approximately omega naught, right? Near omega naught. So this is, I should not say approximately, this is near, this is in band. Correct? So which essentially means that if you take a band pass filter, which is RLC band pass filter will not give this because it's perfectly linear. If you use op amps and all, and if you apply this, and you apply two tones, Vp sine omega 1t and Vp sine omega 2t, where omega 1 and omega 2 are near the center frequency omega naught, then you are going to see the regular terms. You're going to see one here, which is a linear term, but another one somewhere here, right? And the strength of that term will not get attenuated by the profile of the band pass filter. It's well within the band, and the strength of the term with respect to the fundamental gives you the distortion terms. So these type of terms are called intermodulation terms. So this 2 omega 2 minus omega 1, these are called intermodulation. right? So intermodulation makes sense, right? You have two terms which are getting multiplied with each other. Multiplication is effectively, in communication parlance, called modulation, hence intermodulation term. Okay. These are commonly used in RF systems, mostly, because in RF systems, you almost always have narrowband systems. Certain frequency bands are allocated to a carrier. You cannot go here and there. So this intermodulation way of characterizing distortion in RF systems is very common. So if you look up data sheet of amplifiers which are supposed to be working under RF configurations, these becomes an important specification. Okay. Okay, fine. We'll stop here then.